Okay, let's get started. So don't pick up any more homeworks. The homeworks will be there when you come back, I promise. Okay, let's start with some announcements. Most important announcement is, of course, next class is the... okay, first of all, how many people got my mail about Kleinberg and his Kleinberg's talk? Okay, on Blackboard, did anybody succeed in getting my message about the talk? Okay, so hopefully that channel works. I'm going to send out another Blackboard message sometime over the next couple days to remind you of the exam, and in particular, because this room is going to be very full, I have gotten an auxiliary room for the midterm. So if your last name begins with an A through an H, you're not going to be meeting in here. You're going to be taking the midterm in room Social and Behavioral Sciences. That's the building right over there. Okay? On the south side, room 328. Okay? This is 1/3 of the class. 1/3 of the class will be moved here for this midterm, a different third for the next midterm, a different third for the final, so hopefully it will all work out. But this way everyone will have more space and be more comfortable. Any questions about that? What room do people whose last names begin with A through H, what room do they go to take the midterm? For which building is it? It's Social and Behavioral Sciences. Which room number? South 328. This is now posted on the webpage, and I will try to send an announcement over Blackboard, but show up to the right place. Any questions? This way it'll be more comfortable in here. Yes?
On the day of the midterm, could you post if your name starts with A through H on the...
Okay, I will try to, okay. If you don't know that your name begins A through H, you can't read your name posted on the thing. So so that said, we'll try to post it. There will be a guy reminding you at the door, okay? So try to go to the right room. Any questions about that?
Last name. Right?
Last name, by last name. Any questions? Okay? Again, it'd be better if we had a bigger room. We don't have a bigger room. This is what we're going to do. Any questions? So thanks for your patience there. Other stuff about the midterm, just to make sure we're understanding each other. Midterm will be 5-ish problems of the size of a homework problem. Okay, drawn from chapters, most of them will be drawn from chapters 1 through 4. Okay, there will be a couple perhaps that are not drawn from there, and I'm free to do such things. How do you study? I recommend you learn how to solve problems. Practice solving problems. Make sure you understand the idea of the problem. When you write it down, make sure you write what your idea is in English, big blinking idea, and then any details you have to give in pseudocode or something like that. Okay? A big mass of pseudocode that doesn't mean anything, we won't know how to interpret, and that will be bad. Any questions about that? Yes, question. The solutions are now posted for the homeworks. So if you want to go there, the solutions are posted for the homeworks. What? Homework 1, yes. Homework 2, no. Okay? Homework 2 is, it still has to be turned in. So there is no homework 2 solutions posted. Any questions? Yes?
Is there going to be any kind of review for the exam?
Is there any kind of review for the exam? Not really. I may at the end of today ask people if they want to ask a particular question or not, but I'm not planning a special review session for the exam. Okay? That's why we have a course. Okay? Any questions? I mean, so that my instinct is no. Sorry about that. Any questions? Okay? Okay, so let's go through the problem of the day and then the new stuff. This problem of the day is actually very interesting. We've been talking about, last class we talked about quicksort. And this problem of the day, well, okay, maybe I've just given you a hint, okay, is going to be sort of associated with quicksort in an unusual way. The problem has to do with sorting nuts and bolts. What is a nut? Okay, a nut in this context is the kind of hexagonal screw thing that you have seen. Right? This is what a nut looks like. This is what a bolt looks like. It's got threaded screws, right? Nuts and bolts screw into each other. Does everybody know what I mean by this? Is there anybody who's confused by what I'm saying, like they don't know what a nut or a bolt is? Okay, this is a good question if you don't know what it is because you speak a different language or you've never been to a hardware store or anything. So nuts are these round things that screw on at the end of bolts. And every nut has a particular size, specified by the size of the hole, the diameter of the hole. Every bolt has a size specified by the diameter of the bolt itself. So certain nuts screw on and fit on certain bolts. If you have a nut that is too small for a bolt, it just dunks off it. You can't get it on, right? It won't fit. If you have a bolt that is too big for a nut, you know it's too big, but you don't know by how much it's too big. All you know is that it's too big. Does everybody get that idea? So the problem is this. You are given as input a pile of N bolts. Okay, these are bolts. You are given as a pile of N nuts. There is one nut that fits each bolt. And the problem really here is to try to match up the nuts and the bolts efficiently in a world where each nut fits exactly one bolt. Any questions about what the problem is? Okay? So how can we do this? So I guess there's two problems in particular. We want an algorithm, first of all, to match all the nuts with all the bolts. How can we do it? If I give you N nuts and N bolts, and I want to pair up the nuts and the bolts, can anybody give me a worst case algorithm for this? You in the back there, because
compare each nut with each bolt.
There are N nuts, compare each nut to each bolt. If it's too big, it's too big. If it bunks off it doesn't fit. If it screws in perfectly, it's the one that you want, right? Does everybody agree that with N squared comparisons, for each nut, try each bolt, find till they match, that is an N squared algorithm for pairing nuts and bolts? Any questions about that? That should be obvious. Now, suppose I want to find the smallest nut and the smallest bolt, okay? How can I do this with, let's say here it says 2n minus 2 comparisons, or at least let's say a linear number of comparisons? Yes?
You pick one bolt and then you pick up another bolt and compare one smaller, you keep the one smaller.
So say I pick an arbitrary nut and I pick an arbitrary bolt, right? And I try them. No, what am I doing? Tell me what. Pick up two bolts. Now the question is, can you compare two bolts? The answer is no. The only way you can compare things are by comparing nuts to bolts. You hold up two nuts, you can't tell. You hold up two bolts, you can't tell. Okay? The only way you can do it is by comparing a nut to a bolt, and either it bunks off it because it's too small, it grounds it completely if it's too big, or it screws in perfectly. That's the only comparison you can do. How can we do this if all we can do are the nut versus bolt comparisons? Okay, any idea? Yes?
Compare an arbitrary nut and bolt and choose whichever one is smaller to keep comparing to the opposites.
Okay, does everybody see? We can take a nut and a bolt and we try to screw them in, and one of two things is going to happen. Either they're a pair, or one is bigger than the other, right? What he is saying, if one is bigger than the other, you toss the bigger one out, right? You will be left with either a nut or a bolt, okay? And when you do this, you will, you'll be left with either a nut or a bolt. Now you compare it against one of the other ones in the pile. Is that right?
Yes.
What do you do if they happen to be equal?
Depending on your algorithm, you choose either the nut or the bolt to keep the pair, references to the pair, but keep comparing whichever one you pick until either the list ends or you find one. Okay, so what you're saying is if they're the same, you take one of them, put the other one in your back pocket because you might need it later. Okay? Then compare this nut bolt against another new nut. Does everybody see that? Why does that take 2n minus 2 comparisons? Can anyone come up with an argument? Do you know why that takes 2n minus 2 comparisons? Okay, why does that take 2n minus 2 comparisons?
You
You have to compare every item, and there's two sets, so it's 2n, and then if you get to the end and they don't match, it's the last two items, so it's just -2.
Okay, so it should be clear that it's 2n-ish. And why is it 2n-ish? It is because in every comparison, I am either throwing out a nut or throwing out a bolt or sticking in my back pocket, right? But my pile has gotten smaller by 1. Does everybody see that? So the fact that it's 2n seems like that's the 2n part of it should at least be pretty clear, right? That's how many things, and we're throwing them away. It should be clear that at the end, okay, we are happy when we have not thrown out, when we have two things left. Does everybody see that? I think this is the way that I would argue it. Each comparison throws one thing out, okay? We're happy at the end when we have two things left, one nut and one bolt. So 2n minus 2 things get thrown out. Each comparison throws something out. Therefore, that's the right number. Yes? You don't see how it's going to find what? So you're saying it's a correction here. Oh, you're saying your concern is correctness, not efficiency. Okay, fine. So what are we going to do? Let's say implicitly in the world, there is a sorted list. These are the nuts. These are the bolts. Okay? If they were in sorted order, what are we doing implicitly? We are taking a nut, okay? We are taking a bolt. By doing the comparison, we know which of these is smaller, right? We're going to throw out the bigger one, okay, and repeat. We're not going to be content until we have tested every nut or bolt in the process, right? If I compare this, I'm going to keep comparing against this bolt until I get a nut, until I get a bolt that is smaller, right? Once I have that bolt, I'm going to keep comparing it against nuts until I find the nut that is smaller, okay? And kind of my best possibility so far is always going to be the smallest piece of hardware I have seen. Does everybody see that? If I look at all pairs of hardware, all possible pieces of hardware by the end of the algorithm, and I always keep the smallest one that I have seen, then I claim I will find this, keep track of the smallest, find the smallest one. And if there was an equality, the matching element would be in my back pocket. Okay, so that's how I get it. That's my correctness argument. Any questions about that? Okay, do people see that it's 2n-ish, and the plus and minus 2 we'll quibble about? Any questions? Okay, the last one is now the most interesting thing in comparing nuts and bolts, which is pair up all the nuts and all the bolts in n log n comparisons. Okay? Does everybody see that? That's my question now. How can we do it? Okay, yes. Actually, wait, first of all, what does it say? I said n log n, but there was one magic word here that I didn't mention. Which was it? Yeah? Expected. Okay? So that should probably give you some kind of a hint here. Okay? That what do we know about expected? What algorithms would the word expected be a fair thing that we've talked about in here? Quick sort. Okay, so basically what it should smell like, I want to quick sort the nuts and bolts. Okay? Now how do I quick sort nuts and bolts? Now tell me this one. Okay.
So fix a single nut.
Okay, let's try that. Yeah?
Fix a single nut and compare all bolts against it. This will partition the bolts into two sets, less than bolts and greater than bolts.
Okay.
You can see with a nut in a bolt whether one's bigger or smaller.
What do you do with the one?
Okay, so let's take a look at what he has just said, because, it seems interesting. Here we've got nuts, here we got bolts. Pick a bolt as my pivot bolt, is what you're trying to say.
Right.
Here's my pivot bolt, okay? I'm going to compare all my nuts against the pivot bolt, okay? And here I'm going to have all my nuts that are less than the pivot bolt, right? There's going to be one nut that perfectly matches the pivot bolt, and there are also going to be nuts that are greater than the pivot bolt. It should be clear that in n comparisons, I can compare all the nuts against that bolt and break it into those that are less than it and those that are greater than it. And now what do I do? Yeah?
So now you have a bolt you have a nut that perfectly matches the bolt that you've chosen. So you can now partition the bolts based on the nut.
Now I'm going to take the bolt, okay, and go against the nuts. Take the nuts and go against the bolts, right? And all the nuts that are, the bolts that are less than P, okay, meaning less than this nut, are going to go on this side. All the nuts, the bolts that are greater than this nut, go on this side, okay? And now I've got two piles of nuts, okay? Little nuts and big nuts. And I've got two piles of bolts, little bolts and big bolts, okay? And what your next claim is to say, if I'm doing quicksort-like things, you want me to now use the power of recursion. All the matchings between these nuts are going to be those bolts. And all the matches between these nuts are going to be those bolts. We've broken the thing into two smaller problems by the power of recursion, which we can now recursively solve to pair off the bolts, right? We have one matching set, okay? And we have two independent problems that are both smaller than it, okay? And we can now do our quick nut bolt sort, okay, on these recursive things, and that will pair it up. How many people get the idea? Any questions about that? It should be obvious that this is exact same basic analysis as quicksort. The only difference, I guess, we did n comparisons in quicksort, the pivot against n things. Here we're doing the pivot, using the pivot against n things and then the matching pivot against n more things. It's still basically a linear amount of work plus recursion on two halves. And so the same analysis as quicksort goes through here. Does everybody see here? Okay, any questions about this? Now, the reason why this is interesting is this was a simple algorithm. Everybody understands it, okay? Suppose I asked you for a deterministic n log n algorithm for sorting nuts and bolts. You guys hear quicksort and you hear randomized and expected n log n algorithm, okay? And you say, why do I care about an expected n log n algorithm for quicksort, for sorting, when I have heap sort? That's worst case all the time. Absolutely right. This is a problem where there is no elementary algorithm that is deterministic, that will give you no known elementary algorithm that is deterministic for sorting nuts and bolts in n log n time, okay? Where the randomized algorithm is obvious and easy. Does everybody kind of get that idea? Okay? There is a way to do this in n log n using fancy, high-powered machinery that you don't want to know about, or that I don't know, that is complicated, okay? But it should be clear that the randomized solution is pretty easy, okay? And this gets at one reason why randomized algorithms are interesting. Because there often are relatively simple randomized solutions to problems where getting the worst case bound right is hard, okay? Or is either not known or is complicated. Any questions about that? Okay? That's why I like to bring this thing up. This problem actually shows the power of randomization, okay? The fact that you can sometimes find a fast solution, a clean, simple way of solving a problem in a randomized way, which may not be true, okay, deterministically. Any questions about that? Yes?
I came up with a slightly different solution, but I kind of want to know if it's correct or not.
Okay, yes.
If you were to just take the set of nuts and bolts in some order, it doesn't matter. Just arrange them side by side, and then just check if they fit with one of them, so one nut for each bolt. And then after you're done, you'll have some sets that were too small or some bolts that were too small for a nut, and then you have some that fit exactly, and then you have some that were too big for a nut. Could you say that? And now let's say you wanted to find the smallest bolt. Could you take the smaller than bolts and compare them to the nuts that were smaller, that were too small, or?
Okay, I'm not completely sure I'm getting the question, but let me see what I think I can do. Okay, first of all, it sounds like once you are comparing a nut against everything else and using it to divide it into bunches of bigger than or smaller than this, it seems to me you're now in the spirit of what we are doing. Okay? Now, if I wanted to find the smallest nut, I guess maybe if we think about the special case here, suppose I just wanted to find the smallest nut and bolt. Another way I might have done it, which is I think maybe what you're asking, I could take an arbitrary nut, compare it against all the bolts, compare the winning bolt against all the other nuts. Now I know the smallest one is going to lie in this part. Okay? And if I wanted to find the smallest nut and smallest bolt, which was my first question that I asked, maybe I could have done this partitioning step. Okay? Then looked in only this part of the problem. Okay? And try it again. Okay? And then recur on this part. Pick an arbitrary nut, find the matching bolt, split them, partition them, knowing that the smallest pair is always going to be in the smaller side of the partition. That would be a way to find the smallest nut and the smallest bolt. You don't have a good worst case guarantee, because if you got very unlucky, you would always pick as your pivots the biggest nut and the biggest bolt. But in expected case, that's actually not a terrible way to do it. Okay? And in fact, if you pick this one randomly, I think I can argue that that would be order n, expected time. Okay? I don't know if that's what the question is, but if it's not, ask me afterwards. Okay? Yes?
Can you adapt the merge sort method?
Could I adapt merge sort method? Now the trouble here is, the key notion is that I am, so let's think what I'm trying to do. Could I do merge sort on these things? Well, now the problem with doing merge sort, I think here, the crux of the problem is that the base case in merge sort, okay, is I have got one element and one element, okay, and I want to combine the sorted lists of these two. If you pull out one nut, one bolt, and one nut, and I say which is smaller than these two, you can't do it. Because there's no way to compare this nut bolt against that bolt. Does everybody see it? You can only do it if you have the corresponding nuts. And if you have the corresponding nuts, you solved the problem already. Okay? So the problem here is I've got two n things and I can't compare against every other thing. Okay? That's sort of why merge sort is going to break down. Any questions about this? Okay? Hopefully, again, I think it's an interesting problem. It's a cute problem. And it plays on the big idea of randomization. So I talked in here about randomization. I talked here about why quicksort is, should be n log n. The heart of the problem was this, that remember, you're picking a pivot element. The running time of quicksort is going to be governed by basically the height of the tree of partitions you build. Each pivot element in some sense splits everything, creating a binary tree. The height of this tree is what's going to drive the complexity. To get a really tall tree, you have to repeatedly pick pivots that won't do you any good. Okay? In principle, half the pivots are going to be in this nice juicy section that gives you a lot of progress towards partitioning. Breaking it 1/4, 3/4, you've made a lot of progress in one round of partitioning. It is in order to create a big tree, you've got to be very unlucky. You've got to repeatedly pick pivots from this place in sorted order. If you randomly pick pivots, and you always pick the one that's first in sorted order, and then the one that's first in sorted order, and the one that's last in sorted order, and then the one that's first in sorted order, and the one that's last in sorted order, I don't want to stand next to you in a lightning storm, okay? Because it's clear that you're very, very unlucky, right? To pick the worst possible pivot is a 1 in n chance. That's rare. You can't do it that many times. To constantly pick pivots in the bad half, okay? If you picture that half the elements were in the center and half the elements were at the edge, it's like flipping a coin and having it constantly come up tails. You're going to get your coin in any rational universe. The chances, if you have a fair coin, you're not going to get wildly different the number of heads than the number of tails. On any path down the tree, you can't have more than a logarithmic number of heads. If you got this by coin flips, you won't have more than a logarithmic number of tails. That was why it was log n in height. Any questions about that? Any questions about the intuition of why you're playing a game that you're going to win? That's what randomized algorithms are about. Okay? The average thing that happens should be good. Okay? If you pick it randomly. Any questions? Yes?
I have a question. Why is quicksort faster than heap sort?
So why is quicksort faster than heap sort? Okay? So I'll give you a couple answers. First answer is because people tell me so. Okay? If you think about it, all I'm claiming here is I know how to analyze algorithms with a big O complexity, right? Heap sort is n log n, quicksort is n log n, okay? Which is faster? I have my big O analysis can't really tell me, okay? So that's my first answer. A second answer is that people have done a lot of experiments over the years, okay, and so they have shown that quicksort is faster than heap sort, and that's one argument why, okay. You're in some sense maintaining a simpler data structure. All you're doing is, you have a partition of this complicated what's my parent and doing these divisions every time you adjust the heap, okay. So on some level, it's what I am told. If you read Knuth's books, he'll analyze the assembly language very carefully and give you an exact analysis why, okay? But I'm content at my level of knowledge to say, okay, they tell me it's faster, that's what I should probably use. But big O-wise, they're sort of the same to me, okay? Quicksort is 3 times faster, let's say, than heap sort. That's good, okay? I'd rather use, if I have a big thing to sort, I'd rather use quicksort. But on a big O scale, they're within the same noise level, they're the same equivalence class, okay? I can't tell you, okay? Any questions about that? And I'm content with that reasoning. Any questions? Okay? But I want to talk more about what the advantage of quicksort is, okay? Or about randomized algorithms in general. Because this is actually a more important concern. That randomized algorithms not only are easier to analyze, what's interesting about them is that they don't have a worst case in some sense. They don't have a worst case input. They have a worst case running time, but not a worst case input. And this is actually philosophically a very interesting thing. Suppose, let's say, again, if you read the newspapers, you'll know that at this point, if you have the Democrats and the Republicans, they're spending a lot of time trying to embarrass themselves on the budget, right? What would happen if, okay, Obama came up and announced to save a lot of government tax money? He had come up with a deterministic version of quicksort, where he picked used as his pivot element, the last element in the array. And he says, this is the best version of quicksort in the world. I've talked to great computer scientists, okay? It will save us a lot of money, okay? Only in one particular worst case will this run badly, okay? What would the Republicans do immediately? They would say, Obama, you're wasting money again, okay? Sort this particular file. which I have carefully constructed. Suppose, let's say I always pick, let's say, the median element, the middle element in my partition as my pivot, right? Then it could be that there is a particular input where the median element turns out to be the last one in sorted order. Does everybody see that? And after you've done that, this element is going to slide here, and there's going to be a new element in the middle part of the array that happens to be the element that's going to go over there, right? If I give you a quicksort program where you're picking the pivot by some deterministic rule, there is a particular input for which that program will do badly. And the Republicans can go to Obama and say, sort this. And Obama is helpless. Does everybody see that? On that particular input, which shouldn't normally come up in the course of anything else, okay, would have a 1 in n factorial chance of coming up randomly. That input his program will do badly on. Does everybody see that? There is a worst case input. Now suppose instead Obama said, no, I do not have a deterministic quicksort. I am going to pick my pivot element at random. Okay? I'm going to randomly, you know what, you have n elements in the array, I'm going to pick a random integer from 1 to n, and that's the location of my pivot element. Now the Republicans are helpless. Does everybody see that? No matter what bad input they come up with, okay, Obama's algorithm will work every bit as good, okay? He's going to flip a coin, and he might be very unlucky and pick the biggest element as his pivot. And he might then, on the next round recursive call, randomly pick a pivot element and have it be the next largest, right? But note that this is a function of luck, okay? Not a function of the contents of what you are given. This is a big distinction. I want to make sure people see the distinction. Obama would now, the only way this would take a long time is if he got repeatedly unlucky. You don't get to be president by being repeatedly unlucky. Is that clear? Okay? And it changes the game here. What's interesting is that there is no worst case input to randomized quicksort. You can't give me some data that my algorithm is doomed to run slowly on. Okay? If I pick the pivot randomly. If I pick the pivot deterministically, okay, then I am in trouble. Because there is an input file you will give me that I am guaranteed to do badly on. Okay? And this is the difference between a randomized, this is, in some sense, the power of a randomized guarantee. Okay? Note that there is a difference between two different claims you could make. Before, if let's say I used as my median rule, okay, of my pivot rule, always pick the last element in the subarray, okay, before as my pivot element. What you could say is, if you give me the order in random, the randomly permuted data to sort, then when I always pick the last element as my pivot, it will run in expected n log n time. That was the guarantee I give if I give you a deterministic rule. On the other hand, if I give you pick a random pivot element, then what I say is that with high probability, okay, unless you are very, very unlucky, no matter what input you give, my randomized quicksort will run in n log n time. Okay? And this is a much stronger guarantee. Okay? Because it's independent of the input that you're giving me. How many people get this distinction? It's an important distinction. And let's show how important it is. Suppose we use the deterministic rule, where we pick the pivot as always being the last element in the subarray. What is the worst case input to give the quicksort for this pivot rule to do badly? Does anybody know? If I'm always picking the pivot as the last element in my subarray, what would the worst case input be? Yes. Sorted list. If this was 1, 2, 3, 4, up to n. If you always pick the rightmost element, The pivot element here, if I give you sorted order, the pivot beta, the pivot element is the worst possible thing, right? And then what are you going to do when you recur on this half? You're going to pick the pivot, and it's going to be the worst possible thing. Does everybody see that? If I use the deterministic rule, always pick the rightmost element. If the data is sorted, I have a worst case input. Okay? Now, what would probably be the most likely order in practice? Data would come to a sorting program. There's n factorial possible orders. Quite likely some goof already sorted it every once in a while, right? So in this case, the worst case order happens to be something that might be reasonably likely to happen. Okay? But if you took the randomized algorithm, no matter what you did, okay, no matter what data you gave me, the expectation of the running time is the same. Okay? Any questions about that? So this is why randomized algorithms are an important thing. They can kind of make the worst case running time go away and replace it by a sort of expected running time. Any questions? Any questions about randomized algorithms in general? Okay. Occasionally, actually reasonably often, people talk about hashing as a randomized algorithm. Okay, and let's think about to what extent that might be true or not true. Okay? Is building a hash table, okay? You have this hash table, you're going to take this thing mod m and stuff like that. Is hashing a randomized algorithm or a deterministic algorithm? Okay, I'm seeing different hands. What do you think?
Depends on the set of data you're getting.
Okay, if it depends upon the set of data I am getting, then that sounds to me like it's sort of deterministic. Okay, does everybody see that my concern would be, if there is a worst case, it's not really randomized? Does everybody see that if I give you a specific hash function, okay, and my enemy is supplying the data, if they know what hash function I use, there is going to be a set of data such that all those elements go to that same bucket. Okay? So once you fix the hash function, okay, there is a worst case input for it. Right? Question.
It depends on the hash function.
So the interesting question is it randomized or not? It should be clear that if I give you fix the random, if I tell you I print in my code the hash function, then this is not a randomized thing, because someone can read the code of my program and then construct a bad example where everything goes to the same bucket. Is that clear? How many people understand what I mean by this? How many people are confused? Okay, anybody? Let me now confuse you. How can I make this randomized? Okay, I'd like that to be the case. If I am Obama publishing an open source code using a hash function, I would like there not to be a worst case thing for it to come in. What could I do? Yeah?
Instead of using a deterministic hash function, you could just randomly assign a bucket to each item.
Okay, if I randomly assign a bucket to each item, you're right that they're not going to all go to the same bucket, but what's the problem? I don't know where to look for anything, right? If you take all your stuff, you randomly throw it in drawers. Now look for something. You can't do it without searching through everything, right? But what can I do? Yeah. What if at the beginning of the execution of my program, I randomly pick my hash function? Or to be precise, actually, it's actually simpler than that. What if I randomly pick the mod m that I use here? Now my adversary is helpless. Does everybody see that? They carefully chose their examples, okay, assuming I was using a particular hash function. If I use a slightly different hash function, these elements will get tossed in wildly different order. Okay? And in particular, if I pick a hash function at random at the beginning of running my program, then I know where everything is. It's not like I'm randomly tossing them in buckets. I know where it is. I randomly pick my hash function at the beginning, and I'm going to stick with it the whole time, right? But my adversary can't now say, oh, well, I didn't mean to give you that input. Now I meant to give you this input. That's cheating. Okay? So the interesting thing is that this hashing business is also sort of in the randomized world that gives you stronger ideas. Yes?
What if the input was all the same number?
What if the input was all the same number? Well, okay, so with all of our data structures, certainly true that regardless of what the hash table would be, okay, everything would go to the same bucket if they were all the same numbers. With what we've been assuming in all these data structures, we're assuming either that there's no duplicates or there's an auxiliary way to deal with it. So, for example, if I'm dealing with integers and I want, a 1 here is the same as a 1 here, I might as well just count them, right? And instead I have one copy of the integer with a count field of how many times it occurred. And then in that case, my table is only going to have one element in it. Okay? So with all the data structures we've been talking here, we sort of assume that there are no duplicates. Okay? Because either if they're really duplicates, then you might as well just lump them into one. And if they're not duplicates, then they're not, because there's an auxiliary field or so, they will be treated as not duplicates and everything we do here works. Yes?
What if your adversary knows number theory?
What if my adversary knows number theory? Then he's a better person than if he didn't know number theory. But the hard part, again, the basic principle here is, so long as I pick my hash function at random, okay, in some sense there is no particular input that I will be in trouble in. That's the randomized guarantee, and that's why randomized algorithms is an interesting thing. It is easy usually to come up with a randomized algorithm that hides the worst case, okay, and this is a good thing to have. And so, if you take a look at like research in algorithms, a lot of it revolves around randomized algorithms these days because there's interesting guarantees you can get, and this is an interesting area. Any questions about that? Yes?
Would it also be, this wouldn't randomize it, but it could minimize the problem. If you pick the hash function that if you knew its inverse was hard to calculate, could that help?
Okay, so then there's a question you're asking now about how do I make it hard for the bad guy to do this? What if I fix what if I fix my hash function, but I've designed the hash function where, what would I like? If I'm trying to come up with bad examples here, okay, if I want to make an input where everything you get gets hashed to 1, I'd like to be able to now design a set of numbers that would go and hash to 1. Okay? And what you're saying is, maybe there are hash functions where it's hard to do this. Okay, these sort of cryptographic hash functions as they talk about it. So that would make it harder for me to come up with a bad example, right? But on the other hand, if you're Obama, your adversaries are well funded, right? They could take n squared things at random, okay? Hash them. Likely n of them are going to go to the right bucket, to one particular bucket, right? Now if I just give you these elements, they will have all go to the same bucket, okay? So the bottom line is, there's different issues of hash functions that get into some complicated issues. But the big picture is supposed to be clear, that if you do it randomly, okay, you can get a guarantee that is independent of the input. Yes?
If we chose a different, like a random set of functions, then we had like a bunch of constants, like numbers, like values, one could be actual functions.
Okay, you're saying if I had, okay, I'm not sure I'm completely getting the question. It's true that what is true is that if I have a set of hash functions that are possibilities, and I have a set of elements that I'm using, each hash function on all these elements is going to produce a different distribution of values.
Even if they're all the same, all the same.
Well, if all the elements are identical, then again, they're all going to always go to the same bucket. That much should be clear. But if they're all things that happen to go to the first bucket, even though they're by one hash function, even though they're likely to be different, then the odds that in the other hash functions, they're all going to go to the same bucket is very, very small. Okay? Any questions? The details of the hashing thing I don't want, are a little secondary to me. Okay? The bigger picture here is recognize that when you pick a random pivot, or arguably a random hash function, there is no specific input that will give you the worst case. Okay? And that is a good thing. Any questions about that? Okay? That's one reason why the randomized guarantee is relatively strong. Okay? It is certainly stronger than one that puts you at the mercy of the guy saying, oh yeah, give me random input and I'll do fine. Because the world is not like that. The world will not give you random input. Okay? Any questions about that? Yes?
Couldn't two different hashing algorithms do the same output, basically?
Couldn't two different hash functions produce the same output?
Yeah.
The answer is certainly yes. It's certainly true that you could imagine you have a hash function 1 and a hash function 2, and on a particular set of keys, they happen to hash to the same values. But again, if you're picking from a large family of hash functions and you're trying to hash enough things, the odds that that's going to happen are very, very rare. Okay? It's like getting hit by lightning, okay, a couple of times, right? So the basic point is if I have a big enough family of hash functions, which are different enough for most things, and I randomly pick this at the time that I run it, you can't make any guess as to what order will make it hard for me. Okay? Any questions about that? Okay? Fair enough. So that's randomized algorithms. They're a good thing. And again, in general here, we're going to be interested in the worst case. Okay? But this is an important thing to know about in life. Any questions? So again, what is the story? Once you have randomization, the time depends not upon your input, okay, not upon your input, but upon how lucky you are, okay? Depends upon you, that unless you are very unlucky, okay, randomized algorithm will do well. Any questions? Yes?
So is it best just to sort randomized data when you get it?
Is it best to sort randomized data? So it depends what you want to do with this data, okay?
So I mean, when you get the data, to make sure it is random, to sort it once you get it before you. Randomize it once you get it before you sort it.
Okay, so there's another. Okay, so the way I talked about it. So again, there's different ways you might deal with randomization. With randomization. Now, my idea is I'd pick a random integer to serve as my pivot. Okay. Another possibility is you take the data in. Republicans come to Obama and say, here, sort this. It's a nice, innocent data. Obama might just randomly scramble it before he tries to sort it. And that would avoid the same problem. Okay, it's a different way of avoiding the same problem. Okay, any questions? Okay. So what I'd like to talk about, again, I have sort of three different big picture things that I want to talk about today, if I can. One of them was randomization, big picture, important picture. Another thing I'd like to talk about is whether there is a faster way to sort than n log n. Note here I'm asking, is there a way to sort in little o of n log n? Meaning faster than n log n in the worst case. Okay? And we have a bunch of algorithms that sort in big O of n log n. Might there be a faster way to do it? Okay? And what's interesting is that if we limit ourselves to what I will call comparison-based sorting programs, okay, we can think of them as, we can prove that there is no faster way to sort. What do I mean by comparison-based? It means that the basic elements that you're doing are taking pairs of elements and comparing to them. What is it that quicksort does? Okay? Quicksort is poking out a pivot, and it is comparing it right, against another element in the array to decide where to put it, right? It is a comparison-based sorting program. What is merge sort doing? Merge sort was sorted, two lists in sorted order, and what is it doing? It is taking the head of this list and the head of that one and comparing them to see which is better, first in sorted order, right? What is heap sort doing? In heap sort, you add a heap. What do? Well, in order to insert an element in a heap, what are you doing? You are comparing an element to another element in the heap to decide which one should be higher in the heap, right? What is driving all of the algorithms we have talked about is that we are comparing elements against other elements. Okay, and based on, there's an if this is before that in sorted order, do something. Right? Does everybody agree that all the sorting algorithms we have looked at have that flavor? And so if we're going to assume that all sorting algorithms are based on comparisons, then we actually have a proof. I can give you a proof here that there is no faster sorting algorithm than n log n. Okay? And what is the idea here? The idea here is going to be based on the fact that if I have a deterministic program, okay, running the program on the same input is going to cause it to do the exact same thing, okay? But running it on two different inputs had better cause it to do something different, okay? What do I mean? If I think about, let's say, a comparison program for sorting, let's say I think I have 3 integers here, kabunk. When you run your sorting program, you might very well compare the first element in your array against the second element of the array. And depending upon whether that comparison comes out as true, you're going to do something. And if you do something where their A1 is different than is bigger than A2, you're going to do something else. Does everybody see that in any kind of a comparison program, the trace of execution is going to depend upon the input order of what is given? And the program is going to have to somehow do something different. Think what a sorting program is doing. It's rearranging the input, right? If you have 2 different permutations of input and they get rearranged in exactly the same way, the program has to have done something. If the output is the same, the program has to have done something different to move them around. So every program is going to have a different whatever the program is, it's going to have a different execution of comparisons on different permutations of input. How many people sort of see what I'm saying? How many people think it's kind of vacuous still? Okay, no one. Any questions about it? So I want to claim that if that's true, we can think of any sorting program as a tree of comparisons. This tree represents all the possible executions of a sorting algorithm on three elements. How many arrangements of 3 things are there? How many different permutations are there of 3 things? 3 factorial or 6. These leaves each represent a different thing. If the input was already sorted, what did this program do with it? It compared the first input with the second input. First one was less. It compared the second to the third one. The third one was less. That is enough that it figured out that the data was already sorted. The only way those comparisons could work is if the data was already sorted. If, on the other hand, we knew that A1 was bigger than A2, okay, A1 was less than A2, A3 was bigger than A2, then we know that A2 is the last element there, okay? We now compare A1 and A2, depending upon the outcome, we knew it was either this or this. So does everybody see, if you look through this tree, no matter which input it is, this tree of comparisons goes through and figures out uniquely what that sorted order is. And that's in some sense what any sorting algorithm is doing, is figuring out what was the sorted order of the input by doing comparisons. Any questions about that? Okay. Any questions about this model? Like, I don't understand anything in particular. So what is interesting about this? We can now interpret any sorting algorithm as a tree where the leaves, okay, of the tree, it's a tree of executions of the sorting algorithm. The leaves correspond to distinct inputs to the sorting algorithm. The execution of the tree determines the response to that input. The height of the tree is going to be the worst case input of that tree, because each comparison is a step the computer had to do. Does everybody see this? Okay? So in some sense, the behavior of the sorting algorithm is defined by a tree. The tree is going to have height equal to its worst case running time, because the worst case means that it did more comparisons than any other input. Okay? Any questions about that? If you understand, how many people think they understand what I'm saying so far? Okay, good. If you understand this, then the fact that sorting is n log n is going to be very easy. Why is this? We have a tree. How many leaves to sort n things? How many leaves will there be in this tree? Each leaf corresponds to what? Each leaf here corresponds to what? Does anyone? An input ordering, right? How many input orderings are there of n things? N factorial, right? If we have a tree that has n factorial leaves, okay, and we want to make its worst case height as narrow as possible, do we want this to be a balanced tree or an unbalanced tree? Balanced tree, right? What is the height of a tree that is binary tree that has n factorial leaves to it? What is the height of that tree? Log of n factorial. Or in particular, why is that? Because we want to start with one node and double 2, 4, 8. Keep doubling until we have n factorial leaves. Right? So the height of this tree is going to be, if it's perfectly balanced, the log of n factorial. Okay? Does everybody get that idea? That should be clear still. Any questions? If that's true, now the only question is, what is it log of n factorial? And, this is where we start to get into, you have to look at the math and see it. I claim that I can, the easiest way for me to see this is to claim that if I look at n factorial, I want to claim n factorial is less than n to the n and greater than n over 2 raised to the n over 2. Let's think about this. What is n factorial? That's 1 times 2 times 3 times 4 ... up to n. Why is it that n factorial is less than n to the n? Can anybody give me a reason why? Yeah?
So n to the n is n times the product of n.
N to the n is n. If you look at this, one is the product of n. The other one is the product of 1, 2, 3, ... up to n, right? Clearly this guy's bigger. Does everybody see that? What is the log of n to the n? Can anybody think about that? What is the log of n to the n? Yeah? n log n, right? How do you take the log of this thing? You drop the exponent and you take the log of the thing in it, right? Is that how we remember to do it? N log n, right? What is, and this tells me that n log n then is an upper bound on n factorial. Of the log, okay, the log of n log n is an upper bound on the log of n factorial. I claim n over 2 to the n over 2 is less than n factorial. Why is that? Suppose I just consider, here's the world, I have the numbers 1, 2, 3 up to n. If I look at the middle, this is where you get n over 2. All of these terms are bigger than n over 2, right, when you multiply out n factorial. If I just take n over 2, n over 2's, the product of this is certainly going to be less than the product of all of n factorial, right? What is the log of n over 2 to the n over 2? Yeah? It would be, again, I can't, okay, how would I do that? That would be n over 2 gets dropped down, that's the exponent, times the log of n over 2, right? This was a binary term. What is the log of n over 2? Base 2, yeah? Does anyone know what is the log of n divided by 2? If we take the log base 2, yeah?
Log of n minus log 2.
This is the same as log of n minus 1. Okay? Times n over 2. So this lower bound is n over 2 times log n. The upper bound is n times log n. This quantity here has to be theta of n log n. Okay? So this is an argument, the height of the tree, the log of n factorial is n log n. Okay? Therefore, in order to have a sorting algorithm that does n factorial different things, it might have to take n log n time. Okay? And this is an argument that there is no faster algorithm based on comparisons. Any questions about that? Okay, yes?
I mean, I don't think this is likely, but is there a non-comparison based?
Well, is there a non-comparison based, save that question for a minute, okay? Is there a non-comparison based algorithm? The answer is kinda, okay? Maybe. I'll show you something that might be of that type in a minute, okay? But let's still rejoice in what we have here. We have proven that there is no way to sort n things faster than n log n. We've proven in some sense a lower bound on how fast you can compute something and say that there is not a faster algorithm. And this is an amazing thing, okay? In all of computer science, there are very few interesting lower bounds that say absolutely there's no faster way to do it. Sorting is one of them, okay? And this is useful for trying to prove that certain of these data structures you have that sort of could sort, okay, can't be made faster than they are, because if so, they would give you a faster algorithm than you can do, okay? So this starts to prove that several of our data structures can't be made better in the worst case. And it proves, you know, it proves you can't do some things, okay? And even later in the semester when we talk about NP completeness, and we argue there aren't fast algorithms, the guarantees are not quite as strong as they are over here in certain technical sense. Okay, but bottom line, what's interesting is we have proven that there is no faster way to sort, assuming you use comparisons. Yes?
So is the lower bound for that, like, thing that you can approach, is that n over 2
So this proves that this quantity, a lower bound, again, if I think about upper bounds and lower bounds, remember we can think back to our big O notation thing. What am I saying? I am saying that there is a line, a running time line. If we want to look at that here there is a curve. This is n log n. Okay? This is that all sorting, all lower bounds, all sorting programs have to run in at least n log n time. Okay? This is a lower bound on the running time of anything. Okay? That means there is not a faster comparison-based sorting program that's possible. Okay? Which basically, I'm going to show something a little bit weaselly, a little different, but bear in mind that it's sort of a fake. Okay? In principle, n log n is the lower bound on sorting. Any questions? Okay? And so that's a powerful thing. We've proven there is no faster algorithm. But you guys are concerned about the weaselly words I have used, again, about comparison-based sorting algorithms. What might be a non-comparison-based sorting algorithm? Okay? Suppose, let's say, that I am asked to sort, again, I think about it like sorting playing cards. Okay? If those of you play playing, okay. If you sort a deck of playing cards, you're probably, how would people sort a deck of playing cards? I don't know if people have already played playing cards. Okay, there's 52 cards in a deck. There are 4 suits. There are 13, values. Okay? How is it that you would sort a deck of playing cards if I scrambled them up? Would you take each pair of cards, hold them up to each other, and say this one, the 3 of diamonds is ahead of the 4 of things, I'm going to put that there? Or might there be another way you would do it? Okay, how would you do it if you were sorting playing cards? Yes? I would. Actually, if I was sorting exams, that would be a good example. When it comes time at the end, after I see your midterms, we're going to sort your exams. How would I sort my exams? I don't compare each pair of person. Well, McGillicuddy against, against Smith. Okay, put them in that order. What I will do is I will throw them into buckets based on their first letter. Or in the playing cards case, I throw them in buckets based on are they, where they rank in 2 through ace, right? And then I would sort each little bucket, which only has 4 elements, into, queen, diamonds, queens, clubs, hearts, okay, whatever the order of them is. And then push these piles together. Does everybody see that in this case I am not comparing an element against another element? Okay? I am saying I know that the space of keys in this element, okay, have the property that they are 13 different numbers on them. Or I know that when I look up these tests, every one of you guys had to have converted wherever you came from, converted your names into a string of A through Z letters, right? And I could sort them based on the A through Z letters. Okay? Does everybody see how in these cases I am using, essentially I'm building buckets and sorting by buckets. Okay? Instead of comparing elements against elements. Any questions about that? So suppose, let's say, I was given n numbers to sort, each of which were uniformly drawn from 1 to n. How might I sort these n numbers faster than doing an n log n comparisons? Okay? One possibility is, which I'm going to propose here, is I take the space of numbers from 1 to m and draw them into n different buckets, each of which are responsible for m over n of the numbers. The first bucket goes from 1 to m over n. The second number goes from m over n plus 1 to 2m over n, 3n over n, 4m over n, mm over n, or m. Does everybody see how I've partitioned the space of numbers into n buckets? Any questions? If I give you a number, how do I figure out what bucket it goes into? Which bucket does the number 496 go into? How would you compute that? Okay. Yeah?
You would take you would multiply 496 by m, and then divide it by n.
Does everybody see that what I am doing here is, I'm going to want to fit, this is 1m over nth, 2m over nth, 3m over nth. I want to find for my input number x, how many m over nths is it, right? If I multiply that number by n and divide by m, that will give me what bucket it's in, okay? How many people see this? This part's supposed to be easy, and if it's not easy, then I should be asked again. Any questions about that? Okay, do you see what my scheme here is? If each bucket, if let's just think of n over n is too complicated. If this was the numbers up to 100, 200, 300, 400. If I give you a number 496, which bucket does it go into? I would divide it by 100, right? Take the floor of that, I would get 4. And it would be sitting in the 4th bucket. Does everybody see that? So how much time will it take to figure out what bucket it's in? Okay? Constant. It's the time it takes to multiply it and divide it and take the floor, each of which we would say takes constant time. It goes into a bucket. Just like with hash function, if these numbers were uniformly distributed in that range, okay, then there's going to be on average a constant number of people in each bucket. I now scan each bucket from left to right, sort the constant number of people, which should take order 1 time, and just concatenate the buckets left to right. Does everybody see that? And voila, the elements are sorted. Does everybody see how bucket sort works? Okay, a question like I don't see how bucket sort works is a good question. Any questions? Yeah.
Just what's the difference between this and doing making like a bit array?
What is like making a bit array? Well, a bit array is an interesting idea, except that in a bit array you need to allocate as many bits as there are elements in your universe, right? As there are elements in your universe, okay? Meaning these are n numbers from 1 to m, right? Suppose, let's say I wanted to sort billionaires by how many dollars they have, right? Now billionaires will have up to, $100 billion, right? There's only 100 of them, but they've got $100 billion, right? Up to $100 billion. M is 100 billion. N here would be 100. A bit vector would flag. You would set to true the integers which have actually or represent the wealth of a billionaire, right? But you see how you need to have 1 billion bits in order to do that. Here what I've got is, instead I am setting up order n, basically linear in the number of billionaires, buckets, each of which is a linked list, right? Now I've got as many buckets as I have billionaires, right? Okay, yes?
That's, what if you have n values that are close to each other?
Now what happens though, it works great if the numbers are approximately uniformly distributed. Does everybody see that? But what happens if, instead of we design this experiments for billionaires by wealth, and by mistake the billionaires get assigned to a different room and I deal with you guys, right? All of you guys would go, if there were 100 buckets, each of which were of size up to 1 billion, what would be the size of each bucket? 1/100, it's 100, 10 million, I think? 10 million times 100 is 1 billion, right? So everyone here, unless you guys know something I don't, would get assigned to the bucket from 1 to 10 million. And then we've done no sorting. Does everybody see that? This assumes and works well if the data was uniformly distributed. But if it's not uniformly distributed, you could end up in the same bucket. Does everybody see that? Yes.
If it's not uniformly distributed, but you know how it's distributed, can you undistribute it?
You're saying if I know that something about the distribution, okay, can I try to do it? Well, if my distribution is complicated, note that figuring out which bucket I'm going to be in is going to be complicated. Okay? So it is no longer true if you give me a complicated distribution of how people are distributed, if it's not uniform. Yes, there is a spacing of the buckets that will put everybody uniformly, but now it is hard to try to figure out which bucket you belong in. How would I go and figure out what bucket you belonged in? I would do a binary search. And how much time does it take to find the binary search to figure out if I got to add numbers to figure out which bucket I'm in? That would be a log n thing. And now I'm doing n insertions, each of which takes log n time. It's not really, I'm back to my n log n sorting. Yes?
Well, I don't understand. Once you have multiple items, you expect that you have multiple items in each bucket, right?
The assumption would be that if I have n buckets and n items, on average, there's going to be one item per bucket.
What about the situation where there are one?
There certainly are going to be buckets with more than one item, but the assumption is that if these were uniformly scattered, it's just like with the hashing argument. There's not going to be that many items in any one bucket.
How would you deal with sorting that?
So in that case, I'm going to explicitly use whatever sorting algorithm you want on that linked list. If it's of constant size, it doesn't matter. It's going to be, but if there is everybody tossed in the same bucket, then I am in trouble. Okay? Does everybody see what is going on? Okay? If the atoms were uniformly distributed, this should take order n time, but we have no guarantee that they are uniformly distributed. This is the problem that we might have. We might spend linear time tossing it into buckets and learn nothing. Any questions? Yes?
So that would still be n log n?
Well, it depends. You have to now be exactly what you're doing here. If every item got tossed in the same bucket, now you've spent linear time and done nothing. Now you've got to sort them, and it depends upon what you're going to do now. Maybe you'll toss them in another bucket based on, let's say, their second digit. But this can be, you don't know how long this will take. I'd like to end with one cautionary tale, just because I find it example. Thinking about what you know about real-world distributions of names and things like that are complicated. Let's think about how well we know about things like this. In order to try to say we understand our data, suppose you had the job of sorting names in a telephone book. Will you have a lot of skinas or very few skinas? Who here thinks we have a lot? Who here thinks we have very few? Okay, right. We're elite. What about the Smiths? Are there going to be a lot of Smiths in the phone book or a few Smiths? Who here says a lot of Smiths? Says few Smiths. What about Shiflets? Has anybody ever met anybody named Shiflet? You have met a Shiflet?
Yes.
Okay, where did that Shiflet live?
I think it was South Carolina.
Okay, has anybody else met a Shiflet? Okay? If you look at the Manhattan phone book, you will find that there are 10 Shiflets or so. But where I went as an undergraduate, if you look at that phone book in a small town, there are pages and pages of Shiflets in Charlottesville, Virginia. Why is this? Okay? There was some social force where apparently the Shiflets were a clan that fought with another clan in the mountains. They would shoot each other and stuff. And at one point the federal government said, we'll build a dam through them and move the Shiflets to Charlottesville. And so you have a world where a lot of things are not as uniformly distributed as you think. That's the lesson here. Okay? Hopefully one thing that will be uniformly distributed are all your grades on the exam. Okay? But if not, study, work at it, good luck, and I'll see you guys on Tuesday. Thank you.